My dear students, good morning all of you. Today's topic is electrostatics. Here, electrostatics is a branch of physics which deals with the charges at rest. Here, there are two types of charges. One is positive charge and another is negative charge. The electric charge is an intrinsic property of the material particles. That is, the first thing, if you take that introduction, point number 1, electrostatics is a branch of physics which deals with the charges at rest. This is the first point we have. The second one is it helps to study electric forces, field and potential associated with stationary charges. Electric charge is an intrinsic property of material particles. Or matter, you can say. And the fourth one is when an electron is removed from a neutral body, then it becomes a positively charged body. So, electrostatics is a branch of physics which deals with the charges at rest. Second one, it helps to study the electric forces, fields and potentials associated with the stationary charges. Electric charge is an intrinsic property of the material particles. And when an electron is removed from a neutral body, then it becomes a positively charged body. And point number 5, when an electron is added to the neutral body, then it becomes a negatively charged body. So, these are the introductory points related with the electrostatics. Once you got the general idea of the charge, electric charge, then what are the general properties of this electric charges? So, the second one is properties of charged bodies. So, regarding these properties of charged bodies, the first point is when a conductor is charged, then all the charge resides only on its surface, whether it is hollow or solid. So when a conductor is charged, then all the charge resides only on its surface, whether it is hollow or solid. For example, if you consider this is a hollow sphere, and this is a solid sphere, let us assume. Then whenever the charge is given, then all the charge resides only on its surface, whether it is hollow or solid. This is our first point. Then now come to the other one, point number 2. Second point, like charges repel and unlike charges attract each other. Like charges repel and unlike charges attract each other. Suppose this is plus Q1, this is plus Q2, then there exists a force of repulsion. And if they are unlike charge, suppose this minus Q1, this is plus Q2, then there exists a force of attraction. So, like charges repel and unlike charges attract each other. And the third point is an isolated positive charge or an isolated negative charge can exist. So, here there is a point. In case of magnetism, an isolated north pole or an isolated south pole cannot exist. But whereas in the electrostatics, an isolated positive charge or an isolated negative charge can be obtained. And point number 4, charge cannot exist without mass, but mass can exist without charge. So charge cannot exist without mass, but mass can exist without charge. That is, charge is always associated with mass. And point number 5. Point number 5, that is, charge is conserved. That is, the total charge on an isolated system is always constant. This is another point. So charge is conserved. That means the total charge on an isolated system is always remains constant. And next one is charge is quantized. This is another point. So here charge is conserved. Here the charge is quantized. That means The charge on a body is always equals to the integral multiples of the fundamental charge of the electron. That is, the charge on a body is equal to the integral multiples of charge on a body is equal to the integral multiples of the fundamental charge of electron. The charge is quantized this way. That means Q always be given by N, where N is equals to 1, 2, 3, 4 and so on. This small e is the charge of the electron, N is the integer and Q is the total charge. And here the point is 1 Coulomb of charge contains 6.25 into 10 power 18 electrons. Because charge always be expressed in coulombs. Suppose if Q is equals to 1, charge of the electron already known. That is, if you are going to calculate number of electrons, if you want, it is Q by E. Q is 1 Coulomb by 1.6 into 10 power minus 19. That is 10 by 16 into 10 power 19, or otherwise 100 by 16 into 10 power 18, which is equals to 6.25 into 10 power 18. This is how we got it. So clear? So 1 Coulomb of charge contains 6.25 in 10 power 8 electrons. So that is 18. Here Q is 1 Coulomb by charge is 1.6 in 10 power minus 9. These are the number of electrons present in 1 Coulomb of charge. And thereafter, seventh point, point number 7. Charge is invariant. Point number 7, that charge is invariant. What is meant by the term invariant? Invariant means the charge on a body is independent of the speed of the body. That is, the charge on a body is independent of the speed of the body. That is point number 7. And that means, suppose if you are given a question based on that, you may be given a conceptual question like this. That is, a question based on that, you are given like this. A body carrying a charge 2 microcoulombs is moving with a speed 2 into, let us say, 10 power 8 meters per second. What happens to the charge on the body and also mass of the body? Here, whenever you consider this one, a body is carrying a charge of 2 microcoulombs with a speed of 2 into 10 power 8 meters per second. What happens to the charge on the body and also the mass of the body? Generally here, whenever you consider this one, as per this is the, if you take that A bit, the charge on body remains unaltered or remains same. It is simple. So because the charge on a body is independent of the speed of the body. But whereas the other one, what happens to the mass of the body? Mass of the body, when you are here, whenever the objects are moving with a velocity close to the velocity of light, then we must always consider the relativistic mass. That is, according to theory of relativity, relativistic mass mr is equals to m naught by root of 1 minus v square by c square. Here m naught is the rest mass, c is the velocity. If v is close to this one, then what happens? The value will be increased. Therefore, the mass will increases, and thereby the specific charge of electron will decreases. Or otherwise, here, then since if V is close to C, then MR will increases. So mass will increases, whereas the charge on the body remains constant. That is, charge is invariant. And point number 8, charges at rest can produce electric field only. Whereas charges in uniform motion can produce both electric and magnetic fields. Both electric and magnetic fields. Charges in uniform motion can produce both electric and magnetic fields. And next one, charges in accelerated motion can produce not only electric and magnetic fields, but also radiates energy. So charges at rest can produce electric field only. Charges in uniform motion can produce both electric and magnetic fields, and charges in accelerated motion can produce not only electric and magnetic fields but also radiates energy. This is another point. And thereafter, and point number 11, that is electrification. By friction. That is the electrification by friction. Means here, when one body is rubbed with another body, then opposite charges are developed on both the bodies. Thereby, the charges are developed on the neutral bodies. And this phenomenon is called as electrification by friction. But here, which gains positive charge and which gains negative charge can be estimated after several experiments. Some substances are arranged in an order called as electric series. So, electrification by friction means when one body is rubbed with another body, then one body, then the body set time, or then one body gets one body becomes positively charged and other becomes negatively charged. This is called electrification by friction. This is called electrification by friction. Now, some substances are arranged in an order called as electric series. That is, the series of substances So, electrification by friction means when one body is rubbed with another body, then one body becomes positively charged, other becomes negatively charged. And this is called electrification by friction. Some substances are arranged in an order called as electric series. The series of substances are glass, flannel, wool, silk, hard rubber, hard metals, sealing wax, resin, sulfur, etc. Here the point is, if one body is rubbed with another body, one becomes positive charge, we said. So, in this series, if one body is rubbed with other, the former always attains positive charge and the latter attains negative charge. That means, in this series, if one is rubbed with other, that is, in this series, if one is rubbed with other, then the former attains positive charge and the latter attains negative charge. That means suppose if a glass and flannel is used, the glass attains positive and the wool attains negative. Suppose if wool is rubbed with hard rubber, then it becomes positive and this becomes negative like that. So, in this series, if one body is rubbed with another, the former attains positive and the latter attains negative only. Clear? This is electrification by friction. Next one is twelfth one, electrification by conduction. This electrification by conduction means if an uncharged body is kept in contact with a charged body, when an uncharged body is kept in contact with a charged body, then the same polarity is developed on the uncharged body due to conduction. And that phenomenon is called as electrification by conduction. This is called electrification by conduction. Suppose if the third one is electrification by induction. This is another one. Electrification by induction means here when an uncharged body is kept nearer and parallel to a charged body. When an uncharged body is kept nearer and parallel to a charged body, then opposite charges are developed at the nearer ends. When an uncharged body is kept nearer and parallel to a charged body, then opposite charges are developed at the nearer ends. This is called electrostatic induction. That means suppose you are given, you are given a charge, let us say this is plus Q. You can assume like this. And here this is an uncharged body. And here this is the charged body. And suppose this is uncharged body is kept nearer and parallel to this one, then at the nearer ends opposite charges are developed like this. That means on this one, this becomes Q dash. Now you can say that Q is the inducing charge, Q dash is the induced charge. If you are going to find out what amount of charge that is induced on the uncharged body, then we had a formula that is Q dash is equals to minus Q into 1 minus 1 by K, where K is called dielectric constant. Here, for air or vacuum, K is equals to 1. For metals, K is equals to infinity. And for the dielectrics, K value is greater than 1. So this is the point here. Whenever an uncharged body is kept nearer and parallel to a charged body, then opposite charges are developed at the nearer ends. This is called electrostatic induction. If Q is the inducing charge, Q dash is the induced charge, then the induced charge is always minus. This negative sign implies opposite polarity. For air or vacuum, K value is 1. For metals, K is infinity. And for dielectrics, it is K greater than 1. So these are certain important properties of the charged bodies. Then now come to the other one, Coulomb's law. Now come to the other one. This is the next one is Coulomb's law. What is this Coulomb's law? This always states that the force of attraction or the repulsion between two charged bodies is directly proportional to product of the charges and inversely proportional to the square of the distance from the centers. That is, it states that the force of attraction or repulsion between two charged bodies is directly proportional to product of the charges directly proportional to the product of the charges and inversely proportional to square of the distance is inversely proportional to square of the distance between them. This is the statement what you have given. The force of attraction or the repulsion between two charged bodies is directly proportional to product of the charges and inversely proportional to the square of the distance between them. Suppose if you can assume this is a charge Q1, this is the charge Q2, and these two are separated by distance R, then F by above law, F proportional to Q1, Q2, proportional to 1 by R square, or F proportional to Q1, Q2 by R square. This is the relation. Now, suppose if the charges are placed in air or vacuum, then the force is given by the proportionality constant is 1 by 4 pi epsilon naught Q1 Q2 by R square. This is when the present in air or vacuum. Here 1 by 4 pi epsilon naught is equals to 9 into 10 to the power of 9 Newton meter square per Coulombs square. And here epsilon naught is equals to 8.852 into 10 power minus 12 farad per meter. Here epsilon naught is called as permittivity of free space. So if the charges are placed in air or vacuum, then the force becomes 1 by 4 epsilon naught Q1 Q2 by R square. But suppose here, suppose if the charges are placed in a medium, then that F in medium is given by 1 by 4 pi epsilon no, into Q1 Q2 by R square. Here epsilon is called as permittivity of the medium. Is called as the permittivity of the medium. Then once you got the idea of this is in case of medium. Now, what is meant by relative permittivity? And what is meant by our dielectric constant? Relative permittivity or dielectric constant means it is the ratio of permittivity of medium epsilon to the permittivity of free space. Permittivity of the medium to the permittivity of the free space. That is dielectric constant K, derivative constant K is equal to, by definition, epsilon by epsilon naught. This can also be sometimes written as epsilon R. Therefore, epsilon can be written as K epsilon naught or epsilon times epsilon R. And once you got the idea of this, then F in medium, which is given by 1 by 4 pi epsilon Q1 Q2 by R square, can be replaced as 1 by 4 pi epsilon naught K Q1 Q2 by R square. Therefore, F in medium is given by 1 by K into 1 by 4 by epsilon naught Q1 Q2 by R square. Therefore, F in medium is given by this relative force in air by K. This is the relation between the force in a medium and force in air. From this also you can define K is equals to F in air by F in medium. So you can also define that dielectric constant can also be defined in other words as it is the ratio of the force between two charged bodies when they are kept in air to the force between two charged bodies when they are kept in a medium. And here in this case, first thing if you can observe, for air or vacuum, K is equals to 1, hence F in medium is same as F in area. Suppose for metals, if you can observe, K is equal to infinity. Hence, F in medium is 0. That means the conductivity takes place. Because 1 by infinity is 0. Since F in medium is equal to F in air by infinity, something by infinity is 0. And whereas for dielectrics, K greater than 1, hence F in medium is less than F in area. If K greater than 1, this value will be less. So, force in medium is less than force in air. And after that, this is the force. And now, this is the scalar form. What is the vector form of the force? Next one is electrostatic force. In vector form. Electrostatic force in vector form. Here, whenever you consider this is the two charged bodies here. This is Q1 and this is Q2, and these two are separated by distance R. The force exerted by this on this is, suppose if it is taken as F. The unit vector, a scalar quantity multiplied with unit vector in the direction gives the vector component. Therefore, first thing, A bit in terms of unit vector, if I am taking, then F bar is equals to 1 by 4 pi epsilon naught Q1 Q2 by R square into, this is entire scalar quantity. This scalar quantity multiplied with unit vector in the direction gives the vector form. Therefore, F bar can be written as 1 by 4 pi epsilon naught Q1 Q2 by R square. What is unit vector? A vector divided by its magnitude. Therefore, F bar is given by 1 by 4 pi epsilon naught Q1 Q2 by R square, that is R cube into R bar. This is the vector form of the force. And suppose if you are going to calculate in terms of position vector. Both are same, but here the thing is, here if you can consider, let us say two charges. This is a R1 bar, this is a charge Q1, this is the charge Q2, having position vectors R1 bar and R2 bar. Then the force exerted by Q2 on Q1. This is the force on second one due to first one. If we are going to find out, then what is this? That we have to calculate. This is given by, what is the distance between these two? Suppose these two are given, then you can take this is as a points A and this is B. According to triangle law of vector addition, according to this you can take this as R12 bar. I will take like this. Therefore, according to triangle law of vector addition, what you will get? These two are in the same direction, this is an opposite. Therefore, R1 bar plus R12 bar must be equal to how much it is R2 bar. The triangular vector direction always states that if two vectors are represented both in magnitude and direction by the two sides of a triangle taken in the same order, the resultant vector can be represented both in magnitude and direction by the third side of the triangle taken in reverse order. So these two are in the same line. This is in opposite. This will give you the resultant, and therefore R1 bar plus R12 bar is this. Therefore R12 bar can be written as R2 bar minus R1 bar. Therefore F21 bar, this is therefore force exerted by Q1 on Q2 is F21 bar. F21 bar, that is given by 1 by 4 pi epsilon naught Q1 Q2 by R12 square into R12 F. This you can write that as F21 bar is equals to 1 by 4 pi epsilon naught Q1 Q2 by modulus of R2 bar minus R1 bar whole square into R2 bar minus R1 bar by modulus of R2 bar minus R1 bar. Therefore, force on this is given by 1 by 4 pi epsilon naught Q1 Q2 by R2 bar minus R1 bar whole cube into R2 bar minus R1 bar. This is represents the magnitude. Same thing. Suppose if you are asked to find out force exerted by Q2 on Q1, then it is F12 bar. Then we have to take FR22 1 like that. That means that F12 and F21 will be the same. Similarly, force exerted by Q2 on Q1. If you want, it is F12 bar can be written as 1 by 4 pi epsilon naught Q1 Q2 by R1 bar minus R2 bar whole cube into R1 bar minus R2 bar. From this it is clear, this is F12. And suppose if you consider this one, if it is F12 bar. Therefore here, what you can say is that F1 and F2, this is what you are going to. This is the force in terms of vector form. And once you got the idea of this, then what are the properties of electrostatic force? What are the general properties of the electrostatic force? So first one is, it is a conservative force. You know what is conservative force? If the work done by a force around a closed path is zero, then it is said to be a conservative force, which we studied in work power energy. Generally, gravitational force, electrostatic force, Mandy force, elastic force comes under conservative forces. So, electrostatic force or the electrostatic force is a conservative force. The second one is, it is a central force. That means this electrostatic force always acts along the line joining the centers of the two bodies. And the third one is, it always acts along a straight line joining the centers of two bodies, two charged bodies. And point number 4, force between charged bodies depends on the medium in which they are placed. Force between the charged bodies depends on the medium. Depends on the medium in which they are placed. Because F in medium is always equals to F in air by M, F in air by K. So for a different medium, the K value is different, therefore the force. But if it is a gravitational force, then the force between the two bodies independent of the medium that is present. That we'll discuss, which we discussed in gravitation also, that point. And force between the charged bodies depends on the medium in which they are placed. And when multiple charges are given, then the force on any charge due to set of other charges can be obtained by the principle of superposition. When multiple charges are given, then the force on any charge due to set of other charges can be obtained by the principle of superposition. For example, if you are given, let us say here is a charge Q0, here is the charge some Q1, Q2, Q3, like that you are given. Some charges are given. When you have some multiple charges, if you are going to find out the force on Q0, due to this, it is to say F1, because all are repelled this is F2, this is F3, this is F4, and so on. Therefore, net force on charge Q0 due to other charges. According to principle of superposition, it always uses the force on any body due to set of other bodies can be obtained using this principle of superposition, means the sum of all the individual forces. F net is equals to F1 plus F2 plus F3 and F4 and so on. This is in the magnitude terms. Or if you take in the vector form, F1 net is 0. Because here all are same, then we are writing like algebraic sum of all the forces gives the net force on the given charge. So these are some basic, and another one is also given, that is, it always forms action-reaction pair. It forms action-reaction pair. That is, F121 is equal to minus F12. That is forming action-reaction pair. These are the general properties of the electrostatic force. Suppose you may be given a question, two charges Q1, Q2 are separated by a certain distance. What is the ratio of the forces between them? Because it forms action-reaction pair, it is 1:1. 1. Like that we can write. For example, if you are given an example like this, for the sixth one, two charges Q1 and Q2 are separated by a certain distance. Find the ratio of force between them. That means if you have taken these two separated by a distance on, this is Q1, this is Q2, this force is F2 on 1, this is F1, 2. These two are equivalent of, therefore, F12 is to F21, that must be equals to 1 is to 1. Because it forms an action-reaction pair, then the ratio of forces on them is 1 is to 1. So these are the general properties of the electrostatic force. Then come to the other one, that is what is meant by electric field and electric field intensity. What is electric field? That is the space surrounded by a charge in which its influence is felt is called as electric field. Because every charged body will attract or repel the other charged body. Therefore, the force of attraction or repulsion will up to a certain reason. Suppose if you consider this is a charge Q, this will have an attractive property to a certain distance. For example, if you have taken like this, this is the reason up to which the attractive property is existing, is called as electric field. So electric field means the force, the space, not the force, the space surrounded by a charge in which its influence is felt is called electric field. The space surrounded by a charge in which its influence is felt is called as electric field. And here, then what is meant by electric field intensity? That electric field intensity means the force experienced by a unit positive test charge when it is kept in the electric field produced by the source charge is called as electric field intensity. That is, what you can write is the force experienced by a unit positive test charge, the force experienced by a unit positive test charge when it is kept in an electric field produced by a source charge is called electric field intensity. It's called electric field intensity, which is denoted by capital E. So, the force experienced by a unit positive test charge when it is kept in the electric field produced by a source charge is called as electric field intensity. That means here Suppose in this region you are keeping a test charge Q0 at a distance, let us say R. Suppose let Q be the source charge, Q0 is the test charge. Then the force experienced by this is given by force F is given by 1 by 4 pi epsilon naught Q0 by R square. Therefore, but by definition electric field intensity is given by definition electric field intensity is equal to force experienced by the unit positive test charge. That is nothing but 1 by 4 pi epsilon naught Q by R square. This is the electric field intensity. Here, the units for this is, it is given by SI units for this is given by Newton per Coulomb. Is the unit of electric field intensity. And what is the dimensional formula? If you are going to write, dimensional formula for E is nothing but F by Q naught. F is given by ml T power minus 2 by charge is IT. Therefore, it's ml T power minus 3 I power minus 1. This is the formula for the electric field, dimensional formula for electric field intensity. Once you got the idea of this, now this can also be written in the, so if you know the field at any point, then we can easily find out the force by multiplying the charge at that point. And now here, what you are going to get? Vector form of electric field intensity. Vector form of electric field intensity is given by E bar is equals to, that is in terms of unit vector, if I am taking, that is given by E bar is equals to 1 by 4 pi epsilon naught into Q by R cube into modulus of R. Suppose if you want in terms of position vector, it is same like that. This is the electric field. That is in terms of position vector. If you are going to find out E21 bar is equals to 1 by 4 pi epsilon naught Q by R2 bar minus R1 bar whole cube into R2 bar minus R1 bar. This is in the vector form, position vector form of the electric field intensity. Same, only thing if you divide with the charge, we can get the electric field intensity. And thereafter, what is meant by electric line of force? What is meant by this electric line of force? That means an imaginary line or a curve along which an isolated positive charge would free to move in an electric field is called as electric line of force. That is an imaginary line or a curve along which an isolated positive charge would free to move in an electric field is called electric line of force. So an imaginary line or a curve along which an isolated positive charge would free to move in an electric field is called as electric line of force. And here, then what are the general properties of these electric lines of force? First one is for an isolated positive charge, the electric lines of force. The electric lines of force diverges normal to its surface. That is in case of isolated positive charge. Suppose this is a positive charge, then all the lines of force diverges normal to the surface. This is the point. Now the second one is point number 2. For an isolated negative charge, the electric lines of force converges normal to the surface. That is, if you can observe this one, if this is the negative charge, then all the lines of force converges normal to the surface. This is what you are going to get always. If you take this one, this becomes, at every point if you draw the tangent at any point there, it always gives normal to the surface. Third point, in case of an electric dipole, the lines of force starts from positive charge and ends at negative charge. In case of an electric dipole, the lines of force starts from positive charge and ends at the negative charge, normal to the surfaces. And they are open curves. Here is a point that we should remember. In case of a magnetic dipole, the lines of force are closed curves. They start from north pole and they travel from north to south outside the magnet and south to north inside the magnet. Whereas here in this case, if this is a positive charge and this is negative charge, they always travel from positive charge and ends at the negative charge, like this. So they are always open curves. This is point number 3. And point number 4. The tangent drawn at any point on the curve tangent drawn at any point on the curve gives the direction of electric field intensity at that point. Suppose if you can observe this, the tangent drawn at any point. For example, here, if you are given, this is an electric line. Here, if you want this, here is E bar is in this direction. That is EP at point. Suppose if you are going to get here. So, this gives the tangent drawn at any point on the curve gives the direction of electric field intensity at that point. And point number 5, no two electric lines of force, no two electric lines of force intersect each other. No two electric lines of force intersect each other. If they intersect, the field should possess two directions at the point of intersection. Which is impossible. So, no two electric lines of force intersect each other. If they intersect, the field should possess two directions at the point of intersection, which is impossible. And another point number 6, in case of uniform electric field, the electric lines of force are parallel straight lines and are equidistant. In case of uniform electric field, the electric lines of force are parallel, straight lines and are equidistant. Then what is uniform electric field? Uniform electric field means if the magnitude and direction of electric field at every point is same, then it is said to be uniform electric field. In that case, that can represent like this. If the spacing between the lines of force is same, then magnitude of field is same and the direction at every point is same. So, this is considered to be uniform electric field. Non-uniform electric field means if the electric field at a point is different either in magnitude or in direction or both in magnitude and direction, then it is said to be a non-uniform electric field. That means, 7th one, in case of non-uniform electric field, the electric lines of force are as follows. The electric lines of force are as follows. Suppose if you consider this is the first one. Here in this case what happened? All are in the same direction, but The spacing between the lines of force is different. Therefore, here magnitude of E changes, so it is non-uniform. This is magnitude of electric field. Magnitude of electric field intensity changes. In the second case, if you observe this, at every point the direction of field is changing. At different point the direction of, but the spacing is same. So here direction of E bar changes. And third one, in this case both magnitude and direction of E changes. So these are the three cases here. So in case of non-uniform electric field, it is like this. And based on these lines of forces, properties, you may get one question. You may be given a question like this, an example for better understanding. Which of the following lines represents electric lines of force which of the following lines represents electric lines of force for hollow spherical conductor? Suppose you are given like this. Now, what you are going to get here? This is what you are given. Which of the following curves represents the electric lines of force? This is given that here A, B, C, D lines are given. What is A? Here, does A and B will exist? The answer is no. Here, this is not correct, this is not correct, because capital A and capital B are not electric line of force, because no line of force will exist inside the conductor. This is the first thing you can say. Capital A and capital B are not the electric lines of force, because no electric line of force will exist inside the conductor. The second one already we said. Now C is not an electric line of force, because if you draw the tangent at this point, this angle is other than 90 degrees. So, because the line of force enters or leaves normal to the surface. So the line of force neither enters nor leaves. Neither enters nor leaves normal to the surface. Because if you draw the tangent here also, it is other than 90 degrees. But whereas if you draw the tangent for this is making an angle of 90. Here also if you draw the tangent, it is also 90. So, the third one, capital D is the, this is also not applicable, only D. D is the electric line of force because it enters or leaves normal to the surface. Because it enters or leaves normal to the surface. So these are the basic points related to the electric force and field. So what are the different types of questions that may come from this or problems related to force and field will be discussed in the next lecture. Okay, thank you.